create an instant tunnel between two galaxies separated by billions of light years. In mere seconds, you'd zip across distances that light would take an eternity to travel. Sounds like sci-fi, right? But what if I told you that the very math of the universe, Einstein's equations describing the reality all around us, not only allows for this possibility, but actually predicts it? Welcome to the fascinating and controversial world of wormholes. Today, we unravel one of the most intriguing concepts in modern physics. Are wormholes just sci-fi fantasy, or a real possibility predicted by the fundamental laws of the universe? By the end of this video, you'll get how Einstein's math opened the door for these cosmic bridges. Meet the brave scientists who dared to calculate their existence and discover why, even if they're mathematically possible, wormholes might just be the most unstable and impossible to build objects in the entire cosmos. Hey there, cosmic explorers. Welcome to Cosmic Frontiers, where we turn the universe's deepest mysteries into fascinating, easy-to-grasp discoveries. We're on an incredible journey toward our first 1,000 explorers, and every single one of you is a part of this cosmic adventure. To get a handle on wormholes, we first got to rewind to 1915, when Albert Einstein totally revolutionized our understanding of reality with his theory of general relativity. Einstein showed us something extraordinary. Space and time aren't some fixed stage where events play out, but rather a dynamic fabric that can be folded, stretched, and curved by the presence of mass and energy. Picture the universe like a giant trampoline. When you place a bowling ball in the center, the trampoline curves around it. If you roll a marble near the bowling ball, it'll follow the curve created and orbit around it. That's exactly how gravity works. Planets orbit the sun not because there's some mysterious force pulling them, but because the sun warps space-time around it, and the planets simply follow the straightest path possible in that curved space. But Einstein's equations are surprisingly rich and allow for solutions that go way beyond what we observe every day. One of these more exotic solutions was discovered by Austrian physicist Ludwig Flamm just a few months after Einstein published his theory. Flamm realized that the equations allowed for the existence of bridges connecting to distant regions of space-time. Think back to our trampoline analogy. Now, picture having two separate trampolines representing two regions of the universe. A wormhole would be like a tunnel connecting these two trampolines, letting you instantly jump from one to the other without having to cross all the space in between. It's like having a cosmic shortcut that completely bypasses conventional distances. The term wormhole was coined by American physicist John Wheeler in 1957. Wheeler had a knack for coming up with striking analogies, and he pictured these spatial tunnels like the holes a worm makes when burrowing through an apple. Instead of going all the way around the apple's surface, the worm creates a direct tunnel from one side to the other. But here's our first big question. If Einstein's equations allow for wormholes, why aren't we seeing them all over the place? Why isn't there some intergalactic travel agency offering instant trips to Andromeda? The answer lies in the crucial difference between what's mathematically possible and what's physically achievable. The first wormhole solutions discovered by Flamm and other physicists had a fundamental problem. They were inherently unstable. Imagine trying to keep a tunnel open between two mountains using nothing but toothpicks. The moment anything tried to pass through that tunnel, it would collapse faster than the speed of light. This scenario remained unchanged for decades, until two American physicists, Michael Morris and Kip Thorne, decided to tackle the question from a completely fresh angle. It was 1988, and they posed a fascinating question. What if we ignore for a moment whether it's possible to build a wormhole and just focus on how it would have to work if it actually existed? Morris and Thorne weren't trying to prove that wormholes exist, but rather to figure out what conditions would need to be met for them to exist and stay stable. It was like designing a flying car first. You crunch the numbers on how it should theoretically work, then you worry about the engineering challenges. What they found was both exciting and a bit of a bummer. For a wormhole to stay open and traversable, it needs to be propped up by something called negative energy, or exotic matter. But what exactly does that even mean? Let's use a balloon analogy. Imagine you've got a regular balloon full of air. The air inside pushes outward, trying to expand the balloon. To keep a wormhole open, you'd need the equivalent of anti-air that pushes inward, but in such a weird way that it defies our physical intuition. This hypothetical substance would have negative energy density, something that's never been observed in macroscopic amounts in the universe. Negative energy isn't just low energy or lack of energy. It's literally the opposite of energy, like it's possible to have less than zero energy in a region of space. It's like having a temperature colder than absolute zero, something that seems to violate the most fundamental principles of physics. But here's the most intriguing part. Quantum mechanics, which governs the world of subatomic particles, actually allows for tiny amounts of negative energy at microscopic scales. This phenomenon is related to the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. Picture two metal plates super close together in the vacuum of space. Between these plates, certain quantum waves get excluded due to the restricted spacing, creating a slightly negative pressure. It's like the vacuum between the plates weighs less than the vacuum around them. This effect has already been experimentally measured and it's real, but the amounts of negative energy involved are minuscule. To keep a person-sized wormhole open, you'd need colossal amounts of negative energy, trillions upon trillions of times greater than anything quantum mechanics allows. It's like trying to fill an Olympic-sized swimming pool with an eyedropper. Technically possible in theory, but completely impractical in reality. What's more, even if we somehow manage to gather this negative energy, another problem would pop up: fundamental instability. Think about balancing a pencil on its tip. It's mathematically possible, but any tiny disturbance will make the pencil fall. Wormholes are even more unstable than that. Any particle, photon of light, or even quantum fluctuation that tried to pass through the tunnel would create disturbances that would instantly collapse the entire system. It's like trying to keep a giant soap bubble stable during a thunderstorm. No matter how careful you are, it's inevitably gonna pop. But the wormhole story doesn't end there. Some physicists have proposed even more speculative ideas. What if microscopic wormholes were constantly being created and destroyed in the fabric of spacetime, at scales so tiny we can't detect them? And what if advanced civilizations somehow found ways to stabilize these structures using technologies we couldn't even begin to imagine yet? There's also the intriguing possibility that natural wormholes might have formed in the early universe, during the first moments after the Big Bang, when conditions were so extreme that the laws of physics, as we know, barely applied. Maybe some of these primordial tunnels have survived to this day, hidden away in some remote corner of the cosmos. Stephen Hawking, the famous British physicist, even suggested that microscopic wormholes could be part of the fundamental structure of space-time itself, appearing and disappearing on infinitesimal timescales as part of the quantum fluctuations that permeate the universe. There's still another fascinating complication. Even if wormholes could exist and stay stable, they could create time paradoxes. If a wormhole connected not just to distant points in space, but also to different moments in time, we could theoretically travel to the past. This would create the famous time travel paradoxes. What if you went back in time and stopped your own folks from ever meeting? Kip Thorne and his collaborators studied these possibilities in detail and found that the universe itself seems to have built-in protection mechanisms against these paradoxes. Whenever you try to create a setup that would allow for past travel, quantum instabilities pop up that destroy the wormhole before any paradox can even happen. It's like the universe has a cosmic security system protecting causality. This leads us to a deep reflection on the nature of reality. Einstein's equations are like an extraordinarily precise map of the universe, but not everything on the map is necessarily accessible. It's like having a map that shows a lost island in the middle of the ocean. The island might be there, but that doesn't mean we can actually get to it. Wormholes teach us something fundamental about the relationship between math and physics. Math can predict possibilities that nature, by its own deepest laws, chooses not to realize. It's like the universe is a careful writer who, even with access to every word in the dictionary, only picks the ones that tell a coherent and stable story. Currently, the hunt for signs of wormholes remains an active area of research. Some scientists speculate that we could detect them indirectly through their peculiar gravitational effects, or through characteristic signatures in the light passing near them. Others are investigating whether certain cosmic anomalies we observe could be explained by the presence of exotic structures like wormholes. Regardless of their actual existence, wormholes have already given us invaluable gifts. They've expanded our imagination about what is possible in the universe, deepened our understanding of general relativity, and forced us to confront fundamental questions about the nature of space-time and causality. So, cosmic explorers, We've reached the end of our journey through the hypothetical tunnels of space-time. We've found that wormholes represent one of the most fascinating frontiers between what is mathematically possible and what is physically achievable. They simultaneously a demonstration of the elegance of Einstein's equations and a humble reminder that the universe still holds secrets that challenge our ability to comprehend. Perhaps the biggest lesson wormholes teach us is this: our hunger to explore the cosmos knows no bounds. Even when those limits are imposed by the very laws of physics, we're a species that dares to dream of tunnels through space-time, even knowing they might be impossible to build. And that connects us to something deeply human: our insatiable need to explore frontiers, to ask impossible questions, and to imagine realities beyond what we can touch. Wormholes might not exist as usable bridges across the cosmos, but they do exist as bridges in our imagination, connecting what we know today with what we might still discover tomorrow. Maybe the most important question isn't whether wormholes are real, but rather what our fascination with them reveals about ourselves. We're finite beings in a seemingly infinite universe, always looking for ways to transcend our limitations, always dreaming of shortcuts to the stars. Now I want to hear from you, cosmic explorers. If wormholes were real and you could instantly travel anywhere in the universe, what would be your first destination? The center of the Milky Way, an exomoon orbiting a distant planet? Or maybe you'd choose to explore the vicinity of a supermassive black hole? Share your imaginary cosmic adventures in the comments. And since we're talking about unexplored destinations, what other mysteries of the universe would you like me to unravel in the next video? Maybe you're curious about the dark energy that's accelerating the universe's expansion, or about the possibility of life on icy moons like Europa and Enceladus. Drop your suggestions in the comments. You guys are the ones guiding our journey of discovery. Cosmic explorers, we're on an incredible mission toward our first 1,000 members on this expedition through the universe. Every single sign-up gets us closer to forming a true community of folks passionate about cosmic mysteries. If this video expanded your horizons and sparked your curiosity about the wildest possibilities of the universe, join our crew by hitting that subscribe button. Give this video a thumbs up if it made you dream of journeys through space-time tunnels, and share it with someone else who's also fascinated by the limits of physics. In the next video, we've gonna explore another phenomenon that challenges our understanding of reality, and the possibility that our universe is just one among infinite others, each with its own physical laws and possibilities. Until then, keep looking up, keep asking impossible questions, and remember, in a universe where math itself allows for tunnels through space-time, who knows what other wonders still await our discovery.